Pascal triangle intensity ratio and a non-first order H1NMR spectra, it don't follow the Pascal triangle intensity ratio here. And first order spectra values here. So it is somewhat difficult to extract the delta and J values here. And in the first order spectra, the very disadvantage of this disadvantage of your non-first order spectra is, so where the signals are very close and it merges with each other here, and you can see the distortion of the signals. Okay, the signals are very close in the non-first order spectra because the separation, okay, the signal separation is very less because the J values are less than 6 here actually. So less than 6, general J coupling constant value indicates a separation of signals here. The distance between the signals is so J value coupling constant actually. So because the J values are very less, so where the signals are very closer and they will merge to each other, and you cannot means the appearance of the graph or the appearance of this spectra is very clumsy here actually, very complex. And first order spectra, in the first order spectra, the signals are very well separated here, and very clear the spectra is obtained in the first order spectra because the J value is, it is more. So where the distance or the separation of these signals will be takes place here, and the distance between the signals are it is more here. So very neat spectra or the clear spectra will be obtained in the first order proton NMR spectra. And here you see delta nu, nothing but where the difference in the chemical shift, right? Delta in, right? It is a difference in the chemical shifts here, and J is a coupling constant value. So you can calculate that, right? You can. Okay. So here the delta new values are given. New values and J values are given, then you can interpret or you can find out whether it is first order or not first order spectra. Okay. So here is, you see some example here. In this example, you can see where the right, HA and HX. HA proton, it is a HX proton, where the in the where the magnetic right, field, H naught magnetic field is 1.41 Tesla. Instrument, the instrument right, precisional frequency is 1.41 Tesla, and the chemical shifts of HA proton is 60 megahertz, and chemical shift of HX proton is 80 megahertz here, and the J value is 2 hertz. Okay, 2 hertz here. Then you can do the calculation of that. Delta nu equal to where it is a difference of the chemical shift values of your different protons. So delta nu equal to 80 minus 60 by 2. 2 is a J value here, and we got the 10 hertz here. So 10 hertz is, it is more than 6. So it is first order proton NMR spectra. So this spectra obtained very clearly. Okay? And same way you can see the one more example here. So like if you see the example 2, where H1 and H2 protons on, okay, so H1 and H2 protons, where the H1 proton is chemical shift value is 50 hertz here, and H2 proton delta is chemical shift value is 40 hertz here, and the coupling constant, it is 5 hertz here. So then delta nu equal to where the, okay, so 50 minus 40 by 5, where it is 10 by 5 here, so it is 2. So here the Okay, so where this value is 2 means it is non-first order a proton NMR spectra. Okay, so in this way you can find out whether it is first order or the non-first order spectra here. If the chemical shift values and J values are given, so you can calculate the right. So you can find out whether it is first order belongs to first order or the non-first order spectra. So next, the simplification of proton NMR spectra. Simplification of this proton NMR spectra. So this means like conversion of right. So here the simplification of complex spectra. So simplification means with conversion. Okay, the converting the non-first order into the first order spectrum. Okay, conversion of the non-first order into the first order is a simplification of complex spectra here. So for the conversion of this one, for the simplification of complex spectra, we have various techniques here. For the simplification, we have various techniques like increase in the field strength or the instrument frequency. Right. So these are some techniques. You can increase the instrument frequency, and you can simplify that spectra. Either you can convert the non-first order into first order here. And the second technique is spin-spin decoupling, or the double irradiation, or the double resonance. Right. The second method for the simplification is spin-spin decoupling or a double irradiation. And third one is by using the contact shift reagent or the lanthanide shift reagent, LSR. Okay, lanthanide shift reagent. So these are the techniques or the methods to simplify the complex spectra here. Means conversion, where you can convert the complex spectra into simple. The first we'll see the first technique with the increase in the field strength or the instrument frequency. So here, by increasing the field strength or the instrument frequency, so it is possible to increase the separation between the signals. Okay, so if you increase the instrument frequency, then the more absorption of the field strength takes place here. Then where the separation of signals means the absorption of the signals will be takes place with a certain distance here. So this is also one of the technique where by increase of the field strength or the what is your instrument frequency, also you can make the non-first order into first order spectrum here. And the second one is a simplification of a spin-spin decoupling or the double irradiation. This is one of the important technique, important method to follow the simplification of the spectra. So in this particular technique, in the double irradiation, so simple what we are doing in this double irradiation. So like you see, the elimination or the lessening of coupling interaction between the neighborhood protons, like spin-spin coupling. Right. So with the elimination of the interaction, just what we are doing in this double irradiation, just we are doing the means we are removing the interaction. Right. So in general, okay. So with the, for example, here you see your proton is there, and the neighbor proton is there. Okay. Right. Here is the it's B. Let's see, for example, there's 3 types of protons are there, right? So this proton couples with this one, and this couples with this one. Same way, this is also couples with this one. This is couples with this one. Then what in the double irradiation, right? So by applying the more field strength, here, right? So about double irradiation, so we are right, we are removing the interaction of this HB, for example, or the HA, whatever, right? So one of the proton coupling is removed in this double irradiation. We are removing the removing the coupling with the neighboring protons here, right? So then what happens here? So where this proton, right? So it is appears as a blur. Okay. So it is appears as a blur here. So in the spectra, so we'll observe the right signal for this HA proton here, right? You will observe the signal for the HA proton, for example, and you will observe the signal for the HA here, HC, and his B proton is appears as a blur, right? No, you won't observe the signal for the HB proton. Then you can see the separation, right? There is a separation between the HA and CHC protons. Okay, so that is a double irradiation. So where we can removing the spin-spin coupling here, spin-spin coupling, neighboring proton interaction is removed. That is a double irradiation. Right. So here you can see there is two protons are given, like you see. Okay, here is a H1 and H2 protons are there, with irradiating the H2 proton with secondary radio frequency, right? So secondary radio frequency means generally we apply the radio frequency here. Then where by increased frequency, we applied the increased frequency, then it generates the secondary radio frequency. Okay, so where the H1 proton is, okay, you can see in this graph where H1 proton is, it is appears as a clear graph here, a clear spectra, HA proton, and HB proton, there is no signal for the H2 proton here. Okay, so when you irradiate the H2 proton, then it leads to increase of the intensity of H1 proton here. Okay, so double irradiation of the H2 proton leads to increase of the intensity of HA proton, and the H2 proton signal will be, right, it is absent, or you will get a blur, right, noise here, you will get the noise. Same thing, if you, for example, if you are double irradiating your H1 proton, then you will get the signal for the H2 proton here with the double intensity, right, with increased intensity, and H1 proton is obtained as a blur, means blur of these takes place, or with no appearance of the signal for this H1 proton, right? So this technique is used when the spectra is not clear. In that case, right, the spectra visibility of the spectra is not clear here. In that case, we'll do this technique. We'll apply this technique here. Then you will know, means here, for example, if you won't get the clear spectra here, then we have a doubt whether this particular proton is there or not. In that case, what do? You do the double irradiation, then you will get one spectra, right? Means we are blocking the interaction of that. In that case, we get one spectra, one graph, means one signal here. If you get the signal, then we'll know that, we come to know that there is a proton here. If you upon double irradiation, if you won't get the right signal, then there is no proton. So to know whether it is a proton there or not, so we'll do this, we'll apply this double irradiation technique. Okay, and one more example we'll see here. For example, here it right, so let's, okay, in this particular chlorobutanoic acid, okay, here the example we are taken with the chlorobutanoic acid. there is chlorobutanoic acid here. So with their chemical shift values here, okay, so delta 2.2, delta 1.8, delta 3.2. Okay, so for generally this chlorobutanoic acid, it is carrying the three set of protons here. Okay, it is having three set of protons or the three non-equivalent protons here. So we get the three signals for this chlorobutanoic acid. Three signals with their with their multiplicity like okay. So here is this proton. It is giving you a triplet here, and this is obtained as a multiplet. Okay, and this proton obtained as a triplet again. So triplet, multiplet, triplet, and some this acid group. This is also giving one singlet in general in the range of 10 to 12 acid proton. Okay, so you can see if you observe this graph. Okay, we observe the spectra of this chlorobutanoic acid. Right, so yes, right. So at 1.8 we get the multiplet here, pentate, and 2.2 triplet here. There are also triplets. Okay. So when we are doing the double irradiation of this proton, okay, double irradiation of this proton here. So generally it is triplet, so, right? So triplet signal. So we are doing we are double irradiating that. Okay. This way, yes. Okay. Right. So then it leads to increase of the increase of yes. So we are double irradiating this proton here. This, so then where it leads to increase of its signal, and the both triplet signals are going to increase here, right? So the intensity will be increases, and where this CS2 proton signal is becomes blurry here, no appearance of the signal here. Then you can see the clear separation here, right? Here you can see here the separation is less. The gap between the signals is very less here. So when you do the double irradiation of this signal, then you can see the clear separation of this one. Okay. So like that you can means you can choose any one of the group to make that double irradiation here, and then you can see the with improved intensities of that signals here. Right, that is a double irradiation. The only thing is you can apply this secondary magnetic field here. Okay, means for double irradiation, generally the secondary radio frequency is generated, and where it makes that signal blurry here, and it leads to clearance, means clear appearance of your graph spectra. Next, contact shift reagent. The next technique for the simplification of H1NMR spectra is a contact shift reagent. Contact shift reagent, or you could say it is a lanthanide, right? Shift reagent, LSR, lanthanide shift reagent. So in this contact shift reagent method, so where the fractional frequency of sample protons are altered to the different extent by using the chemical reagents, right? So here generally in this particular contact shift reagents, so generally we use the lanthanide complexes here, right? The lanthanide complexes. So where the lanthanide complex whose fractional frequency is more, whose field strength, right, whose fractional frequency more, so it will be transfer its frequency to the reagent, right? Yeah, to that particular compound here. Then that particular protons will be right? The particular protons delta value will be going to increase here. Then it will be appears in the right downfield other downfield other deshielded region, right? Then you can see that separation of that signals is takes place here. So you can see, right? Yes, these are the some lanthanide shift reagents here. Okay, so where the ethenium is taken, and there is a heptafluoro dimethyl octane dione, and right? So for example, here is a compound now. This is your compound, right? So this is your compound where this compound is chelating with your this particular lanthanide, right? So lanthanide means metal, yeah. Okay. Then where the frequency, precious frequency is transferred, right? So because it is chelating with this euthenium here, then it will where the precious frequency is transferred to your compound. Then where they will appears in the downfield region here. So you can see, yes, it is a compound where we are taken like what is this? Yeah, so butanoic acid, yeah, butanoic acid, whose delta values are given. You see, it is okay. So this proton, it is delta is 2.4, and here is 1.4 here, and CSC it is 1.0. So these are the normal butanoic acid del means chemical shift values here. Okay, and if you see the multiplicities H1NMR spectra of this butanoic acid, so without LSR, without lanthanide shift reagent, okay, so where here you get the triplet, multiplet, and triplet. Okay, and when we are added the LSR, lanthanide shift reagent, right? When you add the lanthanide shift reagent here, then you can see the change in the delta values here. Here 1.0 becomes 1.2 here, 1.4 becomes 1.7 here, 2.4 becomes 3.6 here. So what is happening here? Where the separation, right? So separation of the values is takes place. Separation of signal is taking place, right? Where the 2.4, earlier it is at 2.4 here. Now it is 3.6. So you can see the increase in the distance between the signals. Okay, so increase in the distance between the signals is taking place here. So where the complex spectra, it is becoming the simpler here. These are the some techniques for the simplification of the spectra. Okay, yes. And the limitation. So the limitation in the lanthanide shift reagent is, so here the reagent has to be with paramagnetic property here. So generally paramagnetic property means whose delta values are more. Okay. So that reagent, that lanthanide shift reagent, it must have the more delta value here, paramagnetic property. And the selected reagent, it should soluble in NMR solvents. Okay. So it have the property of the solubility in the NMR solvents. NMR solvents are nothing but so many like chloroform, methanol, ethyl alcohol. Okay. And DMSO, dimethyl sulfoxide, DMS, dimethyl sulfide. Right. So these are the, and benzene, carbon tetrachloride. So all these are the NMR solvents here. So these reagents must have the property of the solubility in the NMR solvents, because if they soluble in the NMR solid, then only they will be interact with the reagent compounds here. Then it will be transfer its precision frequency to your compound. Okay. If it is not soluble, it is insoluble, then don't transfer this precision frequency. So the compound must able to soluble in the NMR solvents. And the sample should associate with the electron excessive groups here. So the lanthanide shift reagent, sorry. So your the sample, right? The sample means your compound must having the some right electron excessive groups like hydrogen bonding groups like OH group, NH2 group, SH group, COH group here. Because with the lanthanide, right? The lanthanide shift reagent, it is a metal one where it able to, right?
Sir,
So from the chelation, yes.
sir, we request sir
Mm.
for sharing of sir general chemistry notes.
Mm.
It
Okay,
will be,
I
yes,
will
sir,
do.
if
I will do.
possible, sir.
I will do after class.
Okay, जी, sir. Thank you, sir.
Right. So here the particular uh, sample. Okay. So if the sample is having that electron excessive groups like hydroxy group, amino group, acid groups, the oxide groups here, or any like right. So carbon monoxide groups, CO groups here, carbonyl groups, nitrile groups. So then it able to form the chelation with your lanthanide shift reagent. If the reagent, your compound or the sample is not carrying these such groups here, then it won't form a chelation with your lanthanide shift reagent. Then no contact of your compound with your reagent. So no transferring of the precision frequencies. So that spectra will not become simpler, right? So the limitation for this using of this lanthanide shift reagent is your sample must have right. Your sample must carries all these listed groups here, and the reagent coordinates with the sample and it transfers its magnetic field to the sample protons through intervening bonds or the space. Okay. So generally, this particular sample or your compound is, so it is interacting with the lanthanide shift reagent, and it transfers its precision frequency or the magnetic field here. And the transferring of this magnetic field is either through intervening bonds or through the space here, right? If it is transferring the magnetic field through that intervening bond, right? So it is called the true contact shift here. And if it is transferring the magnetic field through the space, then it is called the pseudo contact shift. So here you can see the, right? So it is, for example, the reagent. Okay. So here is your reagent, and this is your compound. This is your compound. So this particular reagent is transferring it is directly, okay. So it is directly chelates or the forms the bonding with your compound. Then the transferring of magnetic field via intervening bond. Then this is called the true contact shift. And when this particular reagent is not directly forming the bond with this reagent, it is transferring the magnetic field, right, through this space, right, through this space. Then it is called the pseudo contact shift here. Okay. So the requirement is your compound must have the chelating groups here, like hydroxy groups, yeah, alkoxy groups here. Okay. So this is your H1 NMR spectra. And next we are moving to this mass spectroscopy. Right. So here the mass spectrometry, actually the mass spectrometry. So we can't name as a mass spectroscopy, right? For the mass spectra, you can name it is a mass spectrometry or mass spectrum, right? It is not mass spectroscopy. Why we are not using the spectroscopy term for this one is because the source, okay, the source, energy source for this mass spectra is not the EMR here. Here the energy source is the 15 electron volt electron beam here, electrical beam. So the source is not EMR, electromagnetic radiation. That's why you cannot name it as a spectroscopy. You cannot use terms as a spectroscopy here. So you can use a spectrometry. Okay, mass spectrometry. Yes. Yeah. So here the mass spectroscopy. So the fundamental features of your mass spectrometry, where it is not absorption spectroscopy here, right? Generally, it is not a absorption spectroscopy because it is not absorbs any electromagnetic radiation, any radiation here. Okay, so it is not a absorption spectroscopy. And high voltage electron beam, right? Electronic impact is a source, energy source for this mass spectrometry. And if you see the advantages of this mass spectroscopies, spectrometries, where the little quantity of sample is required, right? So for this spectrometry, mass spectra, so you can use very little quantity of compound. Only the microgram compound is required, right? So 0.1 mg is enough for the sample, for the record of the H1 mass spectra, right? And because if you take other spectra, nearly 10 mg, okay, so then nearly 10 mg sample is required. But for this mass spectrometry, so only 0.1 mg to the maximum of 1 mg compound is enough for the recording. And disadvantage of this mass spectrometry is, so generally the sample cannot be recovered. Okay, so once you once you keep the sample in the sample holder, so you cannot recover you cannot get back that sample. like other spectra. If you take C13 spectra and H1NMR spectra, so the sample can be recovered, right? The sample is recovered. So when you keep the sample in the sample holder here, so where the after recording of the H1NMR spectra, the sample will be you can take your sample here. So no loss of the sample. But in the mass spectrum, the sample will not be recovered. There is a loss of sample here. That is a disadvantage of this mass spectrometry. Anyhow, we are not using much sample here, so we are using only the very little sample, like 0.1 mg is very less minute quantity here. So it's not a problem for this one. Okay. Now we'll see the applications of this mass spectrometry. With so it gives exact mass, molecular weight, and molecular formula of the unknown compound by mass spectrometry. So you can find out the molecular formula, means you can derive the molecular formula, and you can find out the exact molecular weight of the compound, and you can calculate the appropriate number of carbons in the compound. Right? So you can calculate the number of carbons in the compound. That is also one of the important. And detection of the heteroatoms like nitrogen, sulfur, chlorine, bromine. So extra elements can be known by this mass spectrometry. Right? And some segments, some fragments will be known by this mass spectrometry, like phenyl, and benzyl aldehyde here, acetyl, nitrile, and hydroxy. So these fragments will be known because you will get some significant or some characteristics, right? Some characteristic signals is obtained for these fragment. Okay, for benzyl you will get the fragment, means you will get the signal at to 91 here. For acetyl you will get the signal at to 43. Okay, for phenyl you will get to 78 here. Okay, so 77. So like that you can right, so easily find out the fragments here, right? So if you find any signal at 91, so you can have the idea about that particular benzyl group here. So if you get the signal at 77, so it indicates, okay, it is corresponding to your benzene group here. So like that, so you can easily find out the fragments by this in this mass spectrum, right? And the heteroatoms like nitrogen, sulfur, all these things will be known by this mass spectrum here, right? So all these are already you are done in the practical sessions. Okay, so you are we done the exercise, mini exercise, and we are derived the molecular formula, and we are find out the extra elements like nitrogen, sulfur. Okay, so we are calculated the dB. So all you are very expertise about these problems here. Okay, so these are the some applications in this mass spectrum here. Okay. Yes, and here like if you see the principle of this mass spectrum, right? The principle of mass spectrum is, so generally in the mass spectrum where the compound, right, the vapor state compound is undergoes the collision with the electron beam. So it undergoes a collision with your electron beam here, and it converts into gaseous state, right? And that particular in this gaseous state, right? So one electron will be removed from your molecule, and it is converting into a new species here, and that new species are the that particular ion. Okay, so it is going to undergoes the fragmentation. Okay, and it gives variety of fragments like negative charged fragments, positive charged fragments, radical fragments, and neutral fragments. So these are the some variety of fragmentation, the possible fragmentations after formation of your radical cation, or we can say it is a molecular ion. Okay, so we can see the scheme of this mass spectrum. So here is a M in the vapor state, means molecule in the vapor state here. So when it is irradiated with the 70 electron volt electronic impact here, so it is converting into molecular ion, and this molecular ion is going to undergoing the fragmentation, and it is giving the variety of fragments, like here is a radical, okay, free radical here, and cation, anion, and a neutral one here. Okay. And but your instrument, it is the only positive charged fragments are useful for the structural illustration, right? Because we'll find means where the signals are obtained for only the fragment, positive charge fragments here. Okay. And the molecular ion, we can say the parent ion here. So where the molecular ion, how the molecular ion is forming here? So generally, when this particular molecule in the vapor state, when it is undergoing the ionization, so one electron is removed from that molecule and it is converting into molecular ion. Okay. And this molecular ion, it is denoted with this particular, right? So M. Okay, so here the M plus dot. It is a wood electron, radical cation here. And generation of the molecular ion here, right? So how to generate the molecular ion here? So here the generation of molecular ion is done by removal of the electron. And while you are removing the electron, generally you have to follow the sequence of this electronic ionization potential, right? So the electron is removed depending on their ionization potential, where the ionization potential is, right? So it is very, so what is ionization potential generally? So the energy required to remove the outer shell electron here, outermost shell electron is called the ionization potential. So with the low ionization IP values, ionization potential. So if you see the order of the ionization potential is where, right? So here the sigma electron IP value is more than pi electron, then lone pair electron. So lone pair electron IP values are less here. Then pi electron IP values are, ionization potential values are, it is medium to the lone pair electron and sigma electron. And sigma electrons IP values are more here. So first you have to remove the lone pair electron if it is there, lone pair electron. Then the second, you can try the removal of electron from the pi bond here. Then sigma electron will be removed. This is the order of removal of the electron, right? So this is the order of removal of your electron from the molecule. Yes. So here you can see the example where here the molecule only with the sigma electrons. There is no pi electrons, there is no n electron here. It is having only sigma electron. So in that case, how to remove the electron and how to generate the molecular ion here. Right? So here is methyl. Okay, so methyl group is taken. So methane is taken here. So generally in the methane, So there is no difference in it because it is having only one carbon here. So you can remove the sigma electron, CH bond electron here. So you can remove any CH bond electron here. So there is no difference in that. For example, if you so take the ethyl, right? So ethyl compound, and we are going to generate the molecular reactant. So in that case, we have the CH bond electron, CH sigma electrons, and CC sigma electrons, right? Right, CH here the CH electron, sigma electron here, and carbon sigma electron. So in that case, so which bond is going to cleave? Which bond is going to cleave in order to generate the molecular ion? Okay. So generally, in that case, right? In that case, you have to remove. In that case, you have to remove the CC sigma electron. Right. So you remove this CC bond electron, not CH here. Okay. Because if you remove the CC bond, then the formed cation is a stable one. Okay, the formed cation is stable. So that's why you prefer to remove the CC bond instead of the CH bond. Yes. So here you can see the upon removal of electron, right? CC bond electron here. So yeah, this electron is removed. Then we are getting this cation here. So you can denote means you can write this molecular ion as positive radical here. Okay, so this is the way of writing of molecular ion. So you can write here C3. Okay, so CSC, CSC, like it. Yeah. So all these are the way of the mentioning writing of your molecular. And the condition, next condition is if the branched hydrocarbon is there, right? If the branched hydrocarbon is there, in that case, which bond electrons need to remove in order to generate the molecular ion. So here is, so you can remove the straight chain carbon bond electron or CH bond electron or the branched carbon electrons. So which one is feasible? Which the removal of electron is feasible here. So in that case, you can see where this particular, right? So this so this CC bond, right? This bond CC bond IP is, it is having low IP value. Okay, and it is having high branched carbon, so you can remove, right? So you can remove the electron from here. Yes. Next, molecule with sigma and pi electrons. So when the molecule is carrying the pi bonds, so obviously you have to remove the electron from the pi bond, right? So undoubtedly, so you can remove the electron from the pi bond to generate the molecule. Here is, you can see in the cyclic compound with the cyclohexene. So here all are the sigma bonds, one is a pi bond here. So obviously you can remove the pi bond electrons and you can generate the molecular ion here. And they generate molecular ion. Okay. And here the molecules are having the sigma and lone pair electron. There is no pi bond. Okay, there is no pi electrons here. In that case, already we have seen the hierarchy of this lone pair electron IP values here, where the lone pair electron is low, high IP ionization potential, then pi bond, then sigma bond. Okay, so lone pair electron should be removed first, and you generate a molecular ion. And the molecule with the sigma, pi, and lone pair electron. In that case, you have to remove the electron from the lone pair electron. That's all. Okay. So all these are the means the preference to remove the electrons when that particular compound is carrying the with the sigma electrons, with pi electrons, or the sigma and pi electrons, and or sigma pi and no electrons here. So this is not required. Yes. So the recognition of the molecular ion and its peaks in the mass spectrum. So this is one of the so recognition of the molecular ion and its peaks in the mass spectrum. So generally in the mass spectrum, the last peak is a molecular ion peak here. Okay. So the last in the mass spectrum, for example, this mass spectrum here, where all the lines means all the fragments lines here. And for example, here is 78 and 70, 74, 64, something 54. All these other values with their m by z values here. On x-axis, we'll take the m by z values, and on y-axis, we'll take the percentage of relative abundance or the percent of natural abundance here. And for example, this is 78 here. So we consider this is the molecular ion. This is your molecular ion. Okay. So in normal cases, okay. So in general, the last peak is the molecular ion. Okay. But it is not means it is not considered. It is not considered always where the last peak in the mass spectrum is not the molecular ion peak. So here, for example, here you see some misleadings in the interpretation of your the mass spectrum, or the identification of the molecular ion here. For example, if your compound is impure, here, then due to the impurity, right? So due to the impurity, it's right. So the way its value will be more, then that will be appears as a last peak here. For example, here benzene is there, then the benzene is 78 here, right? So if it is contaminated with some other impurities here, then benzene is mixed up with some other compound here, so its value will be increases here. Obviously, it will be appears as a last peak here. We thought that this is the molecular ion peak, right? So see that your compound is pure. If your compound is pure, then definitely the last peak is a molecular peak. If it is having any impurities, then the last peak does not be the molecular ion peak here, right? So that is one of the means condition while you are choosing the molecular ion. And the second misleading is here when that particular compound is having the heavier isotopes like chlorine, bromine, iodine, sulfur here. Chlorine, bromine, iodine, sulfur. In that case, the last peak does not be the last peak will not be the molecular ion peak here. Because here you see, for example, here the chlorine is there. Okay. So chlorine, if chlorine is there, so it is having the more molecular weight here. Okay. So you have the ethyl chloride, for example, ethyl chloride, CS3, CS2, Cl, for example, right? So CS3, CS2, Cl, generally the normal chlorine is a 35, right? So it appears at the 66. And if the chlorine is in its isotopic form, then it is appears in the 66 here, 65. Right, the normal molecular ion is appears at 65, but we are getting 66 peak also, right? Along with this 66, we are getting 65. We are getting 66 peak also here. So we should not take 66 as a molecular ion here. It is isotopic peak. Okay. So here also you are given like here C12O16. So C12O16 is a right here the C12O16. This is a normal, right? So molecular ion it is obtained at 28. Okay. So molecular ion it is obtained at the 28. For example, if this carbon is with isotope like C13 here. So you will get a molecular, right? Means the last peak. This will be the last peak here, right? So it's the 28. You can see this is the 28. For example, if carbon is in the C13 form, right? In that case, okay, so this is for this. If it is in the C13 form here, C13, right? Then the last peak will be one more peak, right? Along with this 28. So you'll get a one more peak, 29 peak also. So this is for isotopic. So this is the isotopic peak, but not molecular ion peak here. This is isotopic peak, but not molecular ion peak, right? So that is a condition. So where you see, right? So when you are choosing the molecular ion, when you are finding the molecular ion here, see that the compound, whether the compound is having any isotopes or the compound is in the pure form or impure form here. So the things you have to check. Okay, you confirm whether your compound is okay. You ensure that your compound is 100% pure here. No impurities are there. No contamination is not there, and there is no impurities. There is no isotopes here. In that case, definitely you can choose the last peak as a molecular peak here. Okay. Otherwise, the last peak should not be chosen as the molecular peak if any isotopes are there. Okay. So next, the nitrogen rule in the mass spectrum. This is one of the important question here, which can be asked in the final examination. The nitrogen rule. Explain the nitrogen rule. So very important and very easy also. And already you are right. So well known about the nitrogen rule. So here by this nitrogen rule, so you can find out the number of nitrogens. Okay, the nitrogen rule tells about the number of nitrogens present in the compound here. Okay, so as per this nitrogen rule, if the molecular weight of the molecular ion is odd, then odd number of nitrogens are present here. When number of nitrogens are present. So this is the nitrogen rule. Okay, so here the odd number of right. So mass molecular weight is odd, then odd number of nitrogens are present, and mass is even, molecule is even of, then even are the zero number of nitrogens are present. Okay. So here you see in this example where the aniline. Okay. So here the aniline with the mass molecular is 3. So this is even. Sorry, this is odd here. So odd means definitely there is at least one nitrogen. Okay, there must be at least one nitrogen. So it is having one nitrogen. Okay. And here is dinitroamobenzene here, or orthoamino aniline. So its molecular weight is 108. So it is even mass. So even mass means even number of nitrogens are 0 nitrogens. But it is there are 2 nitrogens. Okay. So like that. And it's a benzene where the mass is 78, even mass. So even mass means there right. So 0 number of nitrogens are even number of nitrogens. but here there is no nitrogen, so no nitrogen. Okay. Yes. And here if you take the toluene here, okay. So in the toluene there is actually, okay. So in the examination they won't give the molecular formula actually, right? They won't give this particular what is that structure or the molecular formula. They will give that. Okay, so one compound is, right. So one compound molecular weight is something like what is this? Only 92 here. Okay, molecular weight is 92, and there are 7 carbons here. Okay, the molecular weight of the molecule is 92 here, and it carries 7 carbons. Okay, 7 carbons. Apply the nitrogen rule to this particular. Apply the nitrogen rule to this particular compound, and find out the number of nitrogens. Right. So they will ask the problem like this. In that case, for example, here the so the molecular weight is 92. Okay, and it is carrying the 7 carbons here. Right. So then, how do you justify that? How do you find out whether the nitrogen is there or not? So you can okay, so you can justify the mass for the 7 carbons here. Right, 7 into 12. Okay, how much it is? 84 here. Okay, and left out is how much it is? 68. Okay, so there are 8 hydrogens here. Okay, so 8 hydrogens are let's say 8 mass is left. Okay, 8 mass is left here. For example, here 92 is a even mass. Okay, 92 is a even mass here. So as per nitrogen rule, okay, so as per nitrogen rule, if we assume the presence of 2 nitrogen here, okay, as per nitrogen rule, if we assume the presence of 2 nitrogen, then its mass will be 28. Okay, and for 7 carbon, it is 84 here. So it is how it becomes how much it is? It is 102, but the mass is total 92 only. So it is exceeding the mass, right? It is exceeding the molecular weight here. So we assume there is no nitrogen here. Okay, so like that. Hence they will ask like this. And one more problem, if you see, the mass molecular weight is, right? The molecular weight of the molecular weight is 90. How much it is? Right. So the molecular weight is 93 here. Right. Molecular weight is 93. 93 with 6 carbons. Right. Then 93 is the odd mass here. So definitely there must be 1 carbon. Sorry, 1 nitrogen. Minimum 1 nitrogen must be there. So for 6 carbon, how much it is? 6 12 here. It is 72. Okay. And 1 nitrogen, it is 28 here. Sorry, 14. 14. It becomes 86 here. So 93, 86, it is 7 hydrogens. So 6, here is a 5 and 2, 7. Right? So like that, how to find out that particular. So yeah, so I'm stopping here. So we will. So I will share the notes, but actually the notes is very lengthy. So you just you go okay, according to your syllabus. Just you keep your syllabus before and you check whatever that material is required. You can sort out that one. Right? Okay. So I'm stopping here.
सर नोट कहाँ पे शेयर करेंगे सर?
ఏమో అది పోయి అలా మ్యాంగో కట్ చేసి వాడతారాబో ఫస్ట్ సార్కి ఇద్దాం కొంచెం సార్కి ఇద్దాం కొంచెం